In this video, we're going to look at Chapter 5, problem number 34. The problem reads, a certain amount of gas at 25 degrees Celsius and at a pressure of 0.800 atmospheres is contained in a glass vessel. Suppose that the vessel can withstand a pressure of 2 atmospheres. How high can you raise the temperature of the gas without bursting the vessel? Well, on first glance, this appears to be an ideal gas problem. So let's see. We write our equation, PV equals nRT. Alright, and now we write our variables that change, so P, V, N, and T, and we start listing them off. So let's see. So 25 degrees Celsius, well that then is 25 plus 273 to convert it to Kelvin, and that gives us 298 Kelvin. So 298, so we just keep knocking them off. Let's keep reading. Oh, look at that, we have 2 different pressures. What do we do? This is the key part of the problem. We look at this, and let's think about this. We have a certain amount of gas at 25 degrees Celsius and at a pressure of 0.800 atmospheres. It's contained in a glass vessel. Alright? We know that there's a gas, alright? And let's call it stage 1, or you could think of it as initial state. So stage 1, we have a gas. It is at 298 degrees Kelvin, and it has 0.800 atmospheres of pressure. Alright? We get, if you read the rest of the problem, we get no more information. We don't get the volume, so no volume, no moles. Alright? So we don't know what those are. The problem then introduces a hypothetical situation. The problem says, suppose that the vessel can withstand a pressure of 2 atmospheres. Alright, it can withstand that. How high can you raise the temperature of the gas without bursting the vessel? This is a hypothetical situation. How much can you increase the temperature to hit this maximum pressure? So we know that at this maximum pressure, 2 atmospheres, that the pressure is going to be 2 atmospheres. Alright? And then the question is, what's this temperature? And once again, there's no mention of volume or moles. Alright, so we have what we're solving for. We know our pressures, but what do we do with these blank spaces for volume and moles? Well, they talk about there's a certain amount of gas. And the only way you fiddle with this certain amount of gas is just to increase the temperature. Well, it tells us it's in the glass vessel, so this is a rigid container. So we know that the volume does not change. We could say like this is V1, well that's a 1, V2, and we could say that V1 equals V2 because it's constant. Likewise, they say there's amount of gas, but they don't talk about adding any more gas, so the moles is also constant. So we have N1 equals N2, or N2 equals N1, whatever you want, they're the same. So for this problem, I think it's just easiest. Let's just cross off these because they're constant. They don't do anything for us. And so we're left with only pressure and temperature. And so the question is, how do we approach this? And the thing is, there's 2 options. Option number 1. Alright, so option number 1. Oh, that's a bad one, sorry. Option number 1 is Charles's law. And Charles's law, the one that deals with pressure and temperature. Alright? And this formula is P1 over T1 equals P2 over T2. Oh yeah, one thing that I probably should have done a little bit before, but because, let's look, this is in stage 1, this is in stage 2. So we'll call this P1, we'll call this T1 because they're the stage 1, and then we'll call these guys P2 and T2. Sorry. Alright? So now we look at this and like, okay, we'll look at this formula, we look at our chart and say, let's fill in the information. So what is P1? Well, P1's 0.800 atmospheres, so 0.800. T1 is 298. Alright, P2 is 2.00, and T2 is what we're solving for. Alright, so now we just cross multiply here, and that gives us 0.800 T2 equals 2.00 times 298. All right? Divide by our 0.800, and we're left with T2 equals 700, is 745 Kelvin. And let's say you want the answer in degrees Celsius, that's the answer they give in the back of the book. You just say 745 Kelvin minus 273 equals 472 degrees Celsius. Alright, but no need to do that, just give it in Kelvin. So, unless the problem states they need it in Celsius, which a teacher might do, so be careful of that. Alright, so we look at that T2, 745 Kelvin. Great, that gives us our answer. Alright, good. Alright, so we figured out how to get the problem answer one way. But now, let's look at option 2, because that Charles's law with pressure, that was nice, but let's say you're in the middle of a test and you forget it. What are you going to do then? Like, you're in trouble then. Don't worry. Let's look at our ideal gas equation. We know that PV, so this is option numero dos. Alright, option 2, ideal gas law. And so this is a way we can use the ideal gas law when we don't, like, only two of the values are changing. And this, I think, is pretty cool. So let's first write what is it. So PV equals nRT. Alright? And using the chart that was on the previous slide, hopefully you have it written down in front of you, let's go through what we had. So, and let's go through it using information from stage 1. Alright, so stage 1. What's our pressure? Well, we know pressure is 0.800 atmospheres. They don't tell us what the volume is, so let's just call it V for volume. Alright, or yeah, let's call it V1 because that's the initial. What's our moles? Well, our moles is N1. Alright, gas constant R is R. And then what's our temperature? The temperature is 298. Alright? Now for this to work, let's put all the things that are numbers that we have on one side. Except even though R is a number because it's 0.0821, let's just keep it by itself. Or not by itself, but on the other side. Because it's always there. So it's not changing. So we do this by dividing by 298. And then the V1 to get the V1 over to the other side. So 298 V1. And so that leaves us with 0.800 over 298 over N1R, oh, not R1. Oops. Alright, I'm stuck with that R1. R over V1. Alright? So that's good. Now, this is where, just trust me, let's go look at stage 2. Alright, so let's make a dividing line. Alright, let's look at stage 2. We start off with our ideal gas law, and let's fill in with the information we get from stage 2. So the only information we have at stage 2 is that the pressure is 2 atmospheres. Remember, we're trying to solve for temperature. So we know that pressure is 2 atmospheres. Volume, we don't know what it is. We'll just say, alright, V2, because we're at stage 2. N2, R, and then we don't know what temperature is, so we'll call that T2. Now notice on this, for stage 1, how I put pressure and temperature by themselves. We want to do exactly the same thing. So we have pressure here, temperature here. We want to divide by temperature and V2 to get pressure and temperature by themselves. Alright, so that leaves us with 2.00 over T2 equals N2R over V2. Now this is where it gets cool. Because let's look at this. We know that this, so 0.80 over 298, that equals N1R over V1. And this over here, 2 atmospheres over T2, that equals N2 V2, or N2 times R over V2. Now this is another key part for using option 2. We know that because the gas is in a rigid container, and they don't really tell us about it, we're assuming that, or we know that the volume stays constant. So in reality, this V1 right here actually equals V2. So here, let's just like scribble those numbers out because they're both the same volume. And likewise, the moles, they don't talk about adding gas or anything. We know that the mole stays the same. So we can scribble that guy out. And then R is constant, so it's always the same. So look at that. We have this thing over here equals this. NR over V. All right? And also, this 2 atmospheres over T2, that also equals then the same thing. And so, like, if I tell you that A, like, let's say the variable A equals 2, and then I also tell you that B equals 2, well, we can then infer that A equals B. I think that's transitive property, maybe? Transitive property? Something like that. This isn't math class, this is chemistry. So we can equate them. So then we can write, okay, 0.800 over 298 equals 2.00 over T2. Now, I know you guys are all freaking out because this is awesome now, because look at that. This is Charles's law. So we kind of, like, solve for Charles's law in this way. It's a lot easier if you just remembered off your head, but look at that. We use the ideal gas law. Oh, not pointer. We use the ideal gas law, worked through all the numbers, set them equal to each other, like got all the variables on one side so we could set them equal, and that gives us Charles's law. That's perfect. So just like last time, we now, option 1, we now just cross multiply, and we find that T2 equals 745 Kelvin. That's great. Great job. So, let's recap. Oh, sorry, I crossed out T, but alright. We were pressed was a situation where we had two different stages. Like, there was the initial state, and then there was this hypothetical situation about bursting the glass. We recognized that these were two stages and filled in the information we had. We only had two pressures, a temperature, and then we were told to solve for a final temperature. We recognized that volume and moles were constant, and so we just crossed them off. In option 1, we remembered what Charles's law was for pressure and temperature, which is P1 over T1 equals P2 over T2, and then we just plugged in our values and solved for it. In option 2, we explored what happened, let's say you forgot Charles's law. How do you solve it? Well, we set up the ideal gas law for stage 1. Plugged in what we had, and then we put all the numbers that were variables on one side that they told us, leaving it equal to NR over V. Likewise, in stage 2, we did the same thing, except now T2 was a variable. We now then realized that by transitive property, I think, we set them equal to each other, and we solved and ended up with Charles's law. So you can use the ideal gas law to like simplify down so you can get these helpful laws in simple expressions. We then solved, found T2 to be 745 degrees Kelvin. And for those of you who are nervous about that doesn't match the answer in the back of the book, don't worry. Back of the book gives it in degrees Celsius. So you take this 745, you subtract 273, and that gives you the 472 degrees Celsius. Hope you enjoyed the video.